Section 1.6 is titled Miscellaneous Equations. So it's kind of a hodgepodge of everything that we haven't seen, but it has relationship to things that we have. So some of the things are going to be similar to what we've seen before, but they'll have different kind of results that happen. And so they're kind of just mushing them all into the same section so that you can consider them all at the same time. So what we see happen is different types, and I'm going to give names to them. So the first type that we're going to do are going to be things that all involve roots, like square roots, cube roots, things like that, radicals, okay? So these are going to involve roots or radicals, but there's different little crazy things that happen as we work with them. Now, if the right-hand side of this had simply been a number, the problem would be quite simple. But because it's an expression, I have an x in it as well as a number, it makes it more complicated. So we definitely do want to get rid of the radical, and we can get rid of the radical, which is a square root, by squaring both sides. On the left-hand side, the square and the square root cancel, which is why we chose to do that, leaving us with x minus 1. However, on the right-hand side, you need to be careful. And this caught you guys, many of you, on the first test. Many of you told me at this point, essentially, that this is x squared minus 7 squared. But that's not true. You have to multiply x minus 7 times x minus 7. That sort of begs the question of, well, why did I get to just eliminate things on the left, but I have to square it all out multiplying on the right? And the reason is because when you multiply with the square root, was it plus or minus? It was minus. Here, x minus 1 times x minus 1, that's actually what happens. There is no distribution. You end up with a square root times a square root, and they're all compacted inside. They're exactly the same quantity. So this is actually going to give you the x minus 1 without having to do any foiling things out. Okay? In a very real sense, what happens is you have x minus 1 times x minus 1 underneath a radical, and you have two groups of things that match, just like we had just like x squareds underneath the radical, and you can pull it out once. We don't have that feature happening on the right-hand side. We don't have a square root. If we did, we could do the same thing, but we don't. So on the right-hand side, we have to multiply the pieces out and distribute. So I have x times x, which would be x squared. So that's my outer terms. My first terms. My outer terms would be negative 7x. My inner terms would be another negative 7x. And my last terms would be the positive 49. Is that okay so far? Okay, lovely. So now we're going to combine like pieces and so forth and continue on. At this point, the problem actually becomes exactly like the problems we were dealing with in the last section. I have a quadratic equation. I have lots of pieces I can combine. This is x squared minus 14x plus 49. And when I have a quadratic equation, I need to get everything on the same side and use one of those variety of techniques I did before. So I can try to factor. If it factors, that's usually my easiest option. You can do completing the square. I don't know anybody who's voluntarily chosen that one at any point in my history teaching. Quadratic equation, the quadratic formula rather, is what people tend to go with when factoring doesn't work. So we're going to move the x to the from the left to the right. We're going to add the 1 from the left to the right. And in doing so, of course, the left-hand sides cancel out by design, leaving me with 0. On the right, I have x squared minus 15x plus 50. Because I have the coefficient in front of the x squared equal to 1, trial and error is a good thing to try if we want to factor. It's usually a nice place to start. If we run into problems with the trial and error, we're welcome to use the AC method, or you're welcome to stop at this point and just use the quadratic formula. In fact, you're welcome to use the quadratic formula if you want to anyway, and that would be fine. This one actually does factor pretty nicely. I have x and x. The positive sign here means my signs have to match, and this negative means the signs need to be both negative. So I need two numbers that multiply to 50 and add to 15. Yeah, 10 and 5 or 5 and 10, either way. And then what we did back in section 1.5 is we set each of these equal to 0. We add our 10. So x is 10. and we add our 5, and so x is 5. Now, if we had been given this quadratic equation right here to start with, like we didn't start where part A started, we started with our next step, the first step that we really had, right? If we'd started here, my answers really would be 10 and 5, and we would be done. The kicker is we didn't actually start there. We started with a radical, and we need to be very careful that the answers that we have actually end up being values that work. Because when you took a square root, you have to be careful about positives and negatives, right? So we want to be careful that the answers we have really work. So in this section in particular, you got to check your work with the original equation you were given. So let's try 10 so you can see how it works, and then we'll try the 5. So if I plug the number 10 into the original equation, I have the square root of 10 minus 1. So that's fine. I have a positive underneath the radical. On the left-hand side, I have 10 minus 7. So what is 10 minus 1? 9, and the square root of 9 is 3. And then 10 minus 7 is 3. So it works for 10. 10 is definitely a solution. No question. Now I need to go back and do the same thing with the number 5. And you don't have to write this out. This is maybe like a scratch work sort of thing, or even if you just want to mentally process through it. But you do need to check them, because this one has a problem. What's 5 minus 1? 2. Well, it's 4, and then the square root of 4 is the 2, right? So we get a 2 on the left. And what's 5 minus 7? Negative 2, and these are definitely not equal. So why did that happen? Well, it happened because the first step that I did in solving this was to square both sides. And if I were to have squared 2 and negative 2, would they in fact be the same? They would, right? So the very process by which I have solved this introduced a solution that doesn't really work. And it happened because I squared both sides, thereby eliminating the potential that one side was positive and one side was negative. So when that happens, this solution is not really a solution. It's actually called extraneous. Sometimes people will say it's an extraneous solution, which really means it's simply not a solution at all. So I want to make sure when I'm giving my answer that I have marked it off. You don't necessarily have to write extraneous, but you do need to designate that it really does not work into the original equation. So we have one solution, x equal 10. The next problem is one where I've used similar questions like this on quizzes and tests. So you might want to star this as a please come back and remember me later, because it causes people a lot of grief because it is a little complicated. I do have two radicals, and that is in fact what makes them complicated. Having the two radicals on the same side makes it really hard. It's easier to work with if I separate the radicals. So I'm going to separate them so the radical's on one side and on the other. So I'm just going to move the one that's negative to the other side. So at this point now I have the square root of x plus 40. And I have, I'll just write it first, not because it matters, but the square root of x and plus 4. So far so good? I don't really do anything, I just moved it. At that point, it looks kind of like the last one, at least in the sense that I've got a square root on one side isolated, okay? So at that point, my process is the same as what I just did a moment ago. I'm going to square both sides. So the left-hand side, again, squaring a square root cancels it out. The problem on the right-hand side is that you've got, again, this temptation to just square the individual pieces. And you can't do that. You have to square all of it. So when I square the x plus 4, square root of x plus 4 times the square root of x plus 4, I have to FOIL things out. And my radical is not going to eliminate in this step. It will later, but it isn't going to eliminate in this step. So as I FOIL out the right-hand side, I'll do my first and my outer. So the first is going to be x. Square root of x times square root of x is x. And then the square root of x times 4, I'll write it as 4 square root of x. And then I have my inner and my last. So the inner terms is another 4 square root x. And then 4 times 4, which is 16. It's not that it's terribly challenging to do the multiplication. What really ends up happening is that people forget in this step that they can't square each individual term. And they do it more often than they do it with this one, because there's a square root that sort of beckons us to want to be eliminated on the right-hand side, right? There is. And we will eliminate it. We just can't do it just yet. So there's two pieces, of course, on the right-hand side that can be combined. I have 4 square root of x plus 4 square root of x. So I'll combine those. So I have x plus 40 equals x plus 8 square root of x plus 16. So much like with the original goal, which was I want to get one of my square roots alone, I want to get this square root alone as well. Okay? So everything that's not a square root on the right-hand side, I'm going to move over to the left-hand side, and some lovely things are about to happen. Because I'm going to subtract the x from the right-hand side, and what's going to happen on the left-hand side? It's going to cancel. So I'm actually going to not end up with another variable x. And I'm going to do the same thing on my 16. It doesn't completely cancel, but it does combine. So these x's go away. 40 minus 16 is 24. These x's go away. And these 16s go away. So on the right-hand side, I'm left with 8 square root x. Again, the goal is to get the square root alone. So what do I do for my next step? Yep, divide by 8. So these eliminate. 24 divided by 8 is 3. And I have the square root of x left on the right-hand side then. What do you think my last step is? Square both sides, you got it. So this is 9 equals x. Now there's still a chance that that doesn't work. Just like on the last problem, I had 2 solutions. One worked, one didn't. I have one, but it could still not work. Yep, Kylie?
You have to add the positive and negative in front of the 3.
No, and the reason you don't is because you're not square rooting, you're squaring.
Oh.
So the positive and negative comes up when we do the square root, not when we're doing squares. All right, so we want to check and see if this 9 now will actually work in what we were given. Original equation before we played with anything. So we'll take this, and we've got the square root of 9 plus 40 plus, no, sorry, it was minus, wasn't it? Yeah, minus the square root of 9. And we want to know if that equals 4. So 9 plus 40 is 49, and the square root of 49 is 7. Square root of 9 is 3. 7 minus 3 is, in fact, 4. So on this one, the solution ends up working. If it did not, let's just say for a moment that it didn't. Put it in, it did not work. It would mean there's no solution to the equation. And it's a viable option, okay? If you only end up with one solution and it doesn't work, then there's no solution that works at all. All right, the next one actually almost looks like it doesn't fit in this section. I do not see initially a root, and I've got it incorporated in the section that said roots. So there is a root there. I cannot remember for the life of me if we've done this in this class or not. I think that we have. But this right here, the 2/3, is called a rational exponent. And it can be written where the 3 becomes the index of the radical, and the 2 stays as the exponent on the x. Have we talked about that in this class? I see some nods. Okay. So we have a cube root of x squared, even though it didn't sort of start out looking like that. This is a root. So we're going to have the cube root of x squared, and it equals 1/2. There are 2 things that I have to eliminate, right? If I'm trying to solve for x, I have to eliminate the cube root, and I have to eliminate the squaring. And while technically you could eliminate them in either order, sometimes one works a little bit better than the other. If the right-hand side had been a very large value, like 512, right? That's a pretty big number. You might want a square root to get rid of the square first to make the 512 smaller. Our value, 1/2, even if you just consider the 2 itself, is not a big number. It's a small number. So we're going to actually do the cubing part first. If you do it in the other order, it won't affect anything. It just might end up being a little bit easier to work with to do it that way. So we're first going to get rid of the cube rooting by cubing. So the cube root and the cube cancel, leaving me with x squared. What is 1/2 cubed? 1 what? 1/8. Okay? 1 cubed is 1, 2 cubed is 8. And then now we are going to take a square root because I need to eliminate the square. So my square and my square root eliminate, leaving me with x. Kylie, I do put on a plus or minus here because I took a square root, particularly a square root. Not like a cube root, but a square root, an even root. So we'll put a plus or minus on this one. And then I have the square root of 1, that's fine. But we need to do the square root of 8. And the square root of 8 is not quite as fine. I mean, it's not a perfect square. So the square root of 8 breaks down into, what does 8 break down into factor-wise? 3 2's. Yeah, 3 2's. So it's 2 times 2 times 2. So 4 and 2, and then the 4 breaks down into 2 and 2. So I have 3 2's. So let me actually just write this to the side so that it's over here. So the square root of 2 times 2 times 2. I'm doing a square root, so I need to have a pair of elements to come out. Right? So this ends up being a 2 on the outside, and then the loner 2 stays underneath. So over here in my original problem, I actually have 1/2 square root 2. But I cannot leave it like that because there's a radical in the denominator. How do we get that square root of 2 radical not in the denominator? You multiply by it. So I will multiply by square root 2 on top and on bottom. So now I have square root 2 on top. This 2 is down here, but these two also combine to give me another 2. Square root of 2 times square root of 2 is 2. That 2 times this 2 gives me a 4. So my solutions, if they exist, I shouldn't box them in yet. I need to check and see if they exist. But my solutions right now, my probable solutions, are positive square root 2/4 and negative square root 2/4. And I need to check and see if they both, in fact, work in the original problem. Okay? And a lot of times when things fail, it's failing because of a positive or a negative. So this comes up a lot with positives and negatives. So we're going to take, and we're going to do it in the form that I rewrote it in, like this one, just because that's how that wasn't actually work. We didn't change anything. We just rewrote it in a different form. So it's a little easier to work with conceptually from there. So I've got the cube root of, we'll do positive first, square root 2/4 squared. So it's your choice whether you do the cube rooting or do the squaring first. Squaring is kind of nice because there's a square root. So I'm going to do the squaring first. And we're running to see if this is equal to 1/2. Sorry. So the square root of 2 squared would give me 2. And 4 squared would give me 16. Right? I don't need the parentheses. And I'm going to have a cube root here in a minute. 2/16 simplifies. How does 2/16 simplify? Yep, it simplifies into 1/8. And is the cube root of 1/8 equal to 1/2? Yes, it is. The cube root of 1/8 is equal to 1/2. So now we want to check and see what happens if I use a negative. So same problem, but we're going to do a negative here and see what happens. So if I have the negative square root of 2/4 squared, what's going to happen to my negative? It's going to become a positive because I'm squaring it, right? So the square root 2 negative will still become a 2, and the 16 will still come apart. I still get a 1/8, and the cube root of 1/8 is 1/2. So both of them do, in fact, work this time. So they both check out as solutions. Any questions on that? Okay, so let's shift gears and look at another type of equation. We've talked about absolute value equations. We did them back in, I think it was like 1.5 or 1 point, or not 1 point, P.5 or P.6. We talked about absolute value equations. But we didn't talk about them where there were quadratics involved. So this is sort of a continuation of that topic from before. So we have an absolute value of the a squared minus 1, and it's equal to 1. Now, we did this before. Anytime we had the absolute value isolated and it was equal to a number, what we did is we set each part, the left-hand side, equal to 1, and the left-hand side equal to what? Negative 1. And if you'll remember, the reason we did that is because if the entire underneath or inside of the absolute value is positive 1, the absolute value of positive 1 is 1. That's this piece. If everything inside a squared minus 1 is equal to negative 1, then the absolute value of negative 1 is equal to positive 1, and that's this piece. Okay, so that's why we did it. We're not changing a positive absolute into a negative. That's not what's happening. We're identifying that the thing that's underneath the absolute value or inside of the absolute value could be positive or negative and still give me an absolute value that's going to equal 1. So we have two solutions. I feel like we should shift them apart a little bit. And they're both quadratic. So this section, once again, reduces to a quadratic type of an equation like we did back in section 1.5. Now, on this, you might notice there are no a terms. You have a squared and you have constants, right? So this actually works very nicely to do square roots on, which was one of the methods that we learned in section 1.5. So we can add the 1 to the side. I have a squared equal to 2. And then what will I do? I will square root. So I put the square root on, which means plus or minus the square root of 2. There are two possible solutions so far. A could equal square root of 2, A could equal negative square root of 2. So those are both things we're going to have to check in a moment. The other one, I add the 1. And what will a squared equal here? 0. And when I square root 0, what do I get? 0. So I get a third solution potentially over here. So there's three possible solutions. So we're going to check them one at a time. Always going to check in this section to make sure that things work. Checking is a good thing to do regardless, but super important in this section. So I have square root of 2 squared minus 1. And the question is, it equals 1. So let's just visually check through it. What's the square root of 2 squared? 2. 2 minus 1 is 1. And the absolute value of 1 equals 1. This works, right? So we're going to do the same thing with negative. Negative square root of 2. So what is the negative square root of 2 squared? 2. 2 minus 1 is 1. And the absolute value of 1 equals 1. So that one worked. So far, two solutions have worked. Let me shift this down a little bit. And then our last one to check is the number 0. So 0 squared is 0. Minus 1 is negative 1. But what's the absolute value of negative 1? 1. So it works as well. So I do, in fact, have three solutions to this absolute value equation. All right? Okay. We're going to do one more absolute value equation. How is this one different than the last one? Yeah, there's an absolute value on both sides, right? Yeah, there is. So there's three possibilities. One possibility is that, ignoring the absolute values for a moment, okay, the left-hand side could be positive and the right-hand side could be positive, right? If that was the case, right, both sides are positive. So well, you can write it down if you want to, but both sides are positive. That's one case. And if that were the case, then if you take an absolute value of a positive, you just eliminate the absolute values, right? Absolute value of 2 is 2. Absolute value of 7 is 7. Absolute value of 492, 492. You eliminate the absolute value. So if that were the case, we would have both sides eliminating the absolute value. So you'd have 2x minus 3 equals 2x plus 7. That's one option. The second option is that they both could be negative. Okay? There's three options. That's the one I chose. This is the second one. I could have I should have value on the left-hand side that's a negative here, that I'm taking the absolute value of. And if you have something on the right-hand side that's a negative, then I'm taking the absolute value of. Agreed? Okay, so if I had a negative, I have to change the signs, correct? Right, the absolute value of -5, I change the sign to be positive. If I have absolute value of -732, I change the sign to be positive 732. So the way that I represent that when I don't have a specific number is I change signs by putting a negative in front of it. Now, I'd like to pause right here for you to recognize, hopefully, that these are the same thing. These two. I still have a third possibility I haven't done yet. But these two are exactly the same thing. Because if I were to divide both sides here by a -1, which is an allowable operation of algebra, I do the same thing to both sides. What will I end up with? The same thing that the other one already was, right? In particular, if this absolute values are equal and they're both negative, well then what's underneath them is already equal anyway. So while there is this case, I never need to consider it because it's equal to the other one I already did. I never have to do that case. The third possibility is that it's actually one positive and one negative. And that's uniquely different, right? If one side's positive, I lift the absolute values. If one side's negative, I actually put the opposite sign on it. And it doesn't matter which one's which, so I can do that arbitrarily. I'm going to leave one side the same, 2x minus 3, so it looks like the one that I did over here. And I'm going to change the sign on the other one, so it'll look like what I did in the middle. So it's going to equal negative, 2x plus 7. So while there are, and you could even say there's 4 cases, it could be that the left one's positive and the right one's negative. It could be that the right one's positive and the left one's negative. It could be the other way around, right? They could be switched. But the point being that they're either the same signs, both positive or both negative, or they're different signs. One side is positive and one side is negative. So it reduces to 2 possible scenarios. The only thing we have to do is these two equations. One where they're both positive or negative, they're the same anyway, and one where their signs are opposite. So I have 2 things to solve. Check out what happens on the first one. If I'm trying to group the x's together, so I try to move what's on the left to the right or on the right to the left, what happens on this particular equation? They cancel, and I'm left with something that doesn't make any sense. Because -3 most certainly does not equal 7, right? So what does it mean? Well, it means that the possibility of this happening where the sides are actually the same side is not possible. This gives me no solution to this side, this possibility. So in other words, the signs cannot match. They're not both positive or both negative. So my other option then is that the signs are different. So I'll solve the second equation. So I have 2x minus 3. We'll distribute the negative. Negative 2x minus 7. And we'll do the same thing. We'll try to get the x's on the same side. So I'm going to add the 2x to the left. And that moves all my x's to the left. And I'm going to move all my constants to the right. So I'm going to add the 3 to the 7 on the right. So these, of course, cancel and cancel like that. So I have 4x on the left. What do I have on the right? -4, and dividing by my 4 will give me -1. I still need to check it, but I do have at least one possible solution that came about from the 2 equations I solved. So we'll check this up here. So I have 2 times -1 plus 3. I'm sorry, minus 3. Apologies. And on the other side, I have 2 times -1 plus 7. So let's check. 2 times -1 is -2. -2 minus 3 is -5. And the absolute value of -5 is 5. On the right-hand side, 2 times -1 is negative 2, plus my 7 is positive 5 now. And the absolute value of positive 5, again, is 5. And notice it did exactly what I said that I was expecting it to do. Inside of the absolute values, they're the same number, but one's positive and one's negative. So I do, in fact, have one solution, and it's x equals negative 1. Okay? So far we've done roots, and we've done absolute values. The last one that we're going to do are called quadratic type solutions. So they're going to look something like a quadratic, but they're not quadratic. So if we take a look up here, we have a power of 4. That makes it not quadratic. I mean, that's just it. It makes it not quadratic. But somehow it looks kind of like a quadratic, doesn't it? It does. It looks like I have something to a power. I've got something in the middle, and I've got a constant at the end. Now, it's still worth looking and seeing, do they have anything in common that I can factor out? These don't, because they could. But it looks like a quadratic. And it actually solves much like a quadratic as well. So because this coefficient is a 1, I'm going to use trial and error just like we did before. You could use the AC method or slide and divide as well if you'd like. But my x to the 4th needs to break down. So normally x squared would break down into x and x. X to the 4th, when it's in this form, will break down into x squared and x squared. And does it make sense that if I take x squared times x squared, I get x to the 4th? Yeah, I do. And I solve the factoring much like I did before. The sign here at the end is positive, so my signs match. The sign in the middle is negative, so my signs have to be negatives. Okay. I need two numbers that multiply to 10 and add to negative 7. So I have 2 and 5, right? Just like the other ones. It's just that there's an x squared in the factoring instead of just x. And I proceed through very much the same way. I have x squared minus 2 equals 0. And I have x squared minus 5 equals 0. They're both quadratic equations at this point. And so I solve them the way I would do a quadratic equation. Because I don't have a linear term again, it's not x squared plus x equals 5, right? It's x squared alone, no other x's. I can use that square root principle that I encountered back in section 1.5. So I have x squared on the left and I have 2 on the right. And I square root. X will equal positive or negative square root 2. And I'll do the same thing with the x squared minus 5. I'll add my 5. X squared is equal to 5. I take my square root. Because I put the square root on, I have to put the plus or minus on. And it's equal to 5, square root of 5. If I had, say, the number 9 here, I could have a plus or minus 3. Right? So I would reduce the radical if I could. These just don't simply don't reduce. You can check these as well, absolutely. The interesting thing about the positives and negatives here is that they cancel immediately because I'm taking things to the power of 4 and I'm taking things to the power of 2, right? So whether it's positive or whether it's negative, I'm going to get a positive value when I do that. So I'm going to consider them kind of at the same time because that feature happens. So if I have, what was my first one? Positive or negative square root of 2 to the 4th, and then I have minus 7 square root 2 squared minus plus 10 equals 0. The square root of 2 to the 4th, well, if I have, like this, that's what square root of 2 to the 4th means. 2 of these are going to equal 2, and another 2 of these are going to equal 2, and then 2 times 2 is 4, so the first piece is 4. And the middle, right here, the square root of 2 ends up being squared to give me 2. So 7 times 2 is 14 plus 10. Does 4 minus 14 plus 10 equal 0? Yeah, it does. So it works. No problem. And I can do the same thing to check out the number 5. So I'm going to just erase my 2's to do that. So I'm going to put the 5s in here. And up here, the same thing. So if I have the square root of 5 times the square root of 5 times the square root of 5 times the square root of 5, two of those together combine to give me 5, and another 5, and then 5 times 5 is 25. In the middle, I have 7 times the square root of 5 squared. Square root of 5 squared would be 5. 7 times 5 is 35. And 25 minus 35 plus 10, does it equal 0? It does. So these were very nice because the positive and the negative didn't have to be considered separately. And again, the reason that they really didn't is because I was taking powers that were even, which eliminate signs, right? They make all things positive when you do that. I think the last one is the most unique looking for today. It looks really messy, and if you actually like multiplied all this out, it would be a lot of work. But what I'd like for you to consider is sort of covering up the part that's in parentheses. Okay? The part that's in parentheses, if it were let to be, let's say, a u. If this said u squared minus 2u minus 3 equals 0 to start with, instead of what it said before, could you solve that? Absolutely, you could solve that. Simple, it's factoring, it's lovely. So let's do that first, okay? We're actually going to solve that. It's one that factors very nicely with trial and error because it's got that coefficient of 1. So I have u and u. This tells me my signs don't match, so I need a negative and a positive. I need two numbers that multiply to 3 and add to negative 2. Multiply to negative 3 and add to negative 2. Negative 3 and positive 1. Okay? And then I can set each of these equal to 0. U minus 3 equals 0. U plus 1 equals 0. And I can solve them because they're linear now too. Right, I can add my 3. So my u is 3. And I can subtract my 1. And so u is equal to negative 1. Okay, everybody good so far? Okay, what I really did is I covered up something else and called it u. Agreed? So the last thing I'm going to do is I'm going to uncover what I covered up, and I'm going to let that again be u. So all of this inside, oh, they were u's to start with. I wasn't paying attention. After I covered them up, I ignored what they were. So sorry, I should have called them x's. Let me change them just real quick so that I don't have the confusion of the double u's going on. Change all your u's to x's. I'm sorry. Okay, so it should have said x's just so that I have a place to make them look different. That was my goal. Not being careful enough. Okay, everything that's circled now in that yellow is equal to that x that I let it be. So this u squared plus 2u is equal to x. So I take the u squared plus 2u, and I replace that with the x, for the x. U squared plus 2u equals 3. And I do it both there and I do it here. So u squared plus 2u is equal to negative 1. Okay? So what did I do? I covered up the complicated part and I made it something simple that I was able to factor and solve very easily. And the piece that was making it complicated, I plugged back in at the end. The nice thing that happens is at the point when I plugged it back in, notice these are simply just two other quadratic equations that we can solve. So we're going to shift things around. The first thing we're going to do is we're going to move everything to the same side. So on the first one, I have u squared plus 2u minus 3 equals 0. It's an awful lot like what I solved a moment ago, right? I can do it with trial and error. I've got u's, my signs don't match. but now I want a positive 2 in the middle, so I have positive 3, negative 1. I set each part equal to 0. So u is negative 3, and u is positive 1. So I have 2 possible answers. I'll come back to check them in a moment. The other one I have down here at the bottom, I'll add my 1 to both sides, but to the left in particular. I have u squared plus 2u plus 1 equals 0. And that also factors. How will that one factor? U plus 1, u plus 1. So you can set them both equal to 0 if you want, but they match, so I'm just going to do it one time. So I subtract my 1, and I have one more possible solution, u equals negative 1. So there's 3 possible answers here. I'll highlight them that we need to check, and we'll check them back in the original equation. So we'll go with negative 3 first, I suppose. Wow, that's not what I meant to click. So I have negative 3 squared plus 2 times negative 3, and I have all of that squared, minus 2 times negative 3 squared plus 2 times negative 3, and then minus 3, and I want to see if that equals 0. That's what I'm checking. And again, you don't have to write check steps out. You're just checking them mentally if you wish, or on a scratch sheet of paper. Yep, Kylie?
When you got negative 1, why in the parentheses would it not be a positive 2 and a positive 1? Because did you factor it?
Yeah, I did factor it, but I factored it so that they have to equal 1 at the end. And the only 2 numbers that multiply to give me 1 are 1 and 1.
Gotcha, okay.
So the factoring was from a different standpoint. Yep. Okay, so it's kind of a mess, but negative 3 squared is 9, plus 2 times negative 3, which would be minus 6. So 9 minus 6 is 3, right? So I have 3 squared here, minus 2 times. The same thing was happening here, so this is another 3. And then minus my 3. 3 squared is 9. Minus 2 times 3 is 6. 9 minus 6 minus 3. That's 0, right? Yeah, it works. It checks out. And then we would check the next one, which was a positive 1. So we have 1 squared plus 2 times 1 in each of the parentheses. So 1 squared is 1, plus 2 times 1 is 2. So I actually have 1 plus 2 is 3. That's 3 squared. I believe that's what I had on the last one, wasn't it? 3 squared minus 2 times 3 minus 3. That one works, right? It does. And then our last one was to check was negative 1. And on negative 1, I have negative 1 squared, which is 1. 2 times negative 1 would be negative 1. So 1 minus 2 gives me a negative 1. So inside those parentheses is actually negative 1 this time. So negative 1 squared is 1 on the first one, right? It's negative 1 squared. Over here I have 2 times negative 1 minus the 3. So negative 1 squared is 1. I have 1 then plus 2 minus 3. Again, it equals 0. So on this one, all 3 of the solutions that were probable at the end of the problem actually worked out. So I have 3 solutions on this one. That one's a hard one, I think. There's a lot of pieces going on, So try to keep your work, as organized as you can. I do all my scratch work on the side so that it doesn't mess up all the other things that are going on. And of course, if the scratch work shows that it doesn't work, then it's extraneous and we mark it out. We saw an example of one of those today. All right, so 1.5, 1.6 are both complete now. and then you will turn those in. One of the two, or maybe both of them, will happen, and I will collect them on Tuesday. Have a great weekend.